Alright, today we're going to be talking about PN junctions with open terminals, so there's no applied voltage. So we first look at the structure, and PN junction stands for P, which is positive, and then N, which is the negative type, and then junction. So you have a P-type side and then an N-type side. In theory, it's supposed to be two different silicon crystals, but in real life, you just dope two sides of a singular silicon crystal to create two different halves. Since the free electrons and the holes can move around freely, but the actual atom is actually in a lattice structure, so it can't be moved around, so it's bounded, then when the free electrons from the negative side goes to the positive side, it will leave behind a positive charge in the N-type side. And it would be vice versa for the P-type side too, where the holes would move to the N-type side, leaving behind a negative charged depletion area. So we'd have electrons going from the N-type side to the P-type side, which would result in the current going from the P-type side to the N-type side, since current is a reflection of the opposite movement of the electrons, which is kind of weird, but that's how it works. So that would create the depletion region, and the depletion region would happen at the contact plane because naturally the electrons closest to the P-type side would move over there, and then vice versa. The depletion width is dependent on the amount of diffusion and its junction built-in voltage VO. So it creates an electric field that acts as a barrier for diffusion. So the more diffusion that happens, the bigger the electric field would be, which would increase the junction bias voltage, which would make it harder for diffusion to happen. So this would slowly build upon itself, and then at the max VO, we would have no more diffusion current. And then on the other hand, we have drift current, which is for the minority carrier current. So the diffusion current is for majority carrier current. So for instance, the N-type side, that would be the electrons that are moving. For drift current, for the N-type side, it's the holes that we're actually concerned about. So for drift current, it's we have this depletion area, and then we also have holes in the N-type side due to thermal influence, because the heat would break up some of the covalent bonds and create holes in the N-type side. So the holes in the N-type material drift to the contact point and drift to the P-type side, and then on the other hand, free electrons in the P-type side would drift to the contact point and drift to the N-type side. So it's actually the opposite of diffusion. So then we would have equilibrium, because we have the drift current going one way and then we have diffusion current going the other way. So equilibrium is when they are equal to each other, and then there's no more current. But if diffusion current is greater than the drift current, VO would constantly increase until we reach equilibrium point. And then on the other hand, if diffusion current is less than drift current, VO would decrease until we reach equilibrium point. And the VO stands for junction built-in voltage, which is VT times the natural log of the concentration of free holes times the concentration of free electrons over Ni squared. So for example, silicon in room temperature, it would be around 0.6 volts to 0.9 volts.